on starting with chapter 1 today, so we have to go with the plan, okay? So chapter 1 is just going to kind of be our introduction to chemistry. It's just going to kind of lay the base layer of what you guys need to know moving forward in the chapter or in the textbook. All right, so number 1, in introducing chemistry, we kind of have to introduce what is chemistry, right? What is chemistry as a science? So number 1, it's a science, so that's good. We already have one definition, but what is it trying to do? What is the entire goal of chemistry? So, ideally, what chemistry is trying to do is it wants to explain the property of matter, okay? What is matter? Matter is anything that has mass, right? And what else? Takes up space, right? Has mass, takes up space, okay? So chemistry's whole goal is to explain how matter behaves, and it's going to do so by understanding and explaining the properties of the atoms and molecules that make up matter, okay? So main goal, we want to understand matter, and we're going to do that by understanding the properties of each individual atom and molecule that makes it up. Okay, so that's nice. What is an atom, though? We haven't really defined that. So an atom is essentially just the fundamental building blocks of matter, okay? So we'll talk about all the various atoms that we have, all the various elements, but right now just note that atoms constitute the fundamental building blocks of matter, okay? Atoms by themselves are kind of unstable, right? You don't tend to find them by themselves in nature. Instead, atoms tend to combine with other atoms to form what are called molecules, okay? So again, I defined atom in the first slide. I'm now talking about what a molecule is. So atom, fundamental building block, molecules are different atoms that have combined together to form a new compound, okay? All right, so what do we mean by this? How can we explain what matter is by understanding the atoms and molecules that make it up, okay? So a good example of that is this molecule carbon monoxide, okay? So has anyone heard of carbon monoxide before? Somewhat. So what do you know about carbon monoxide? Can you say it out loud? It's toxic, right? It'll kill you, okay? What is carbon monoxide made out of? Is this an atom or is this a molecule? It's a molecule, right? It's made out of 2 atoms specifically. It's made up of a carbon atom, wrong one, carbon atom that is bound to another oxygen atom, okay? Again, it is toxic, all right? Why is it toxic though? What does it do, okay? So, to explain that, we have to introduce you to hemoglobin. So what is hemoglobin? Hemoglobin is in your body, right? What does it do in your body? Transports oxygen, right? So how does hemoglobin actually work? So you breathe in oxygen into your lungs, right? So oxygen in your lungs. There are hemoglobin molecules that go through and pick up those little oxygen molecules, right? What do they do at that point in time? They move out to the periphery of your body, so your arms, your legs, etc., to your brain, right? And what happens? Do the oxygen molecules stay on them, or what happens? Eventually they come off, right? Hemoglobin is just the transport molecule that moves oxygen from your lungs to the rest of your body, okay? So again, that's great, but what does it have to do with carbon monoxide, okay? The reason why carbon monoxide is toxic is because it binds to hemoglobin as well, right? So if you breathe in carbon monoxide, it binds to hemoglobin. More importantly, it actually has a higher preference for hemoglobin, right? So if you breathe in a mixture of carbon monoxide and oxygen, the hemoglobin will take up the carbon monoxide first, okay? So it takes up the carbon monoxide. Instead of taking the oxygen to the rest of your body, it takes carbon monoxide to the rest of your body, right? Again, with oxygen, at some point in time, the oxygen molecules popped off, and the hemoglobin went back to your lungs, right? With carbon monoxide bound to hemoglobin, it moves out to the rest of your body, and the carbon monoxide will not pop off, right? So it essentially just takes up all of the spots in your hemoglobin molecules where oxygen would bind, and then it won't release itself. So oxygen can never bind, right? Long term, what happens if you don't have oxygen? You suffocate, you die, essentially, okay? So this is why carbon monoxide is toxic. This is exactly what it does, okay? Now, I want you to contrast carbon monoxide, which is just, again, a carbon and an oxygen, to carbon dioxide, right? So carbon dioxide is a carbon, but how many oxygens does it have attached to it? 2 oxygens, right? So we have now 1 and 2. So carbon dioxide, toxic, bad, took up all the spaces on your hemoglobin. What do you know about carbon dioxide with respect to human toxicity? Is it toxic? No. What do we breathe out when we breathe out? CO2, okay? So this is a good illustration of what we mean by trying to understand the property of matter by understanding the atoms and molecules that make it up, right? What have we done to carbon monoxide when we've converted it to carbon dioxide? All we've done is add 1 extra oxygen. But what has that done to the overall properties of the molecule? It's changed them drastically, okay? So just 1 little oxygen can take something that was toxic to something that is harmless and something that we actually breathe out every day of our life, okay? Another good example of that is the difference between water and hydrogen peroxide. So what is water? It's a molecule, again, right? What are the atoms that make up the molecule water? So we have an oxygen and we have 2 hydrogens, right? Do you drink water? Ideally you should drink lots of water, but do you drink water? Yeah. Do you bathe in water? Do you wash your hair? Some days, some maybe. What about hydrogen peroxide? What is hydrogen peroxide made up of with respect to atoms? We have 2 oxygens now, and we have 2 hydrogens. So all we've done is added 1 little oxygen into this molecule comparatively to water, okay? Can you drink hydrogen peroxide? If you bathe or you wash your hair in hydrogen peroxide, what would happen? It would bleach it, right? So again, the addition of 1 little atom changes the properties of the molecule entirely. The goal of chemistry is figuring out why. Like, why is hydrogen peroxide corrosive? Why is it bad comparatively to water? Why is carbon monoxide bad compared to carbon dioxide? This is kind of be the goal of what we're trying to do with respect to chemistry, okay? Okay, so again, this kind of just recapitulates what I just said. If we want to understand matter, we have to understand the atoms and molecules that make it up. We'll spend a lot of time this semester understanding these atoms and molecules. Okay, so chemistry, how do we do chemistry? So chemistry is a science, right? And most importantly, it is an empirical science. So what does empirical mean? It's based on, instead of being based on just feelings, it's based on observation, right? So empirical means it's something that is based on what you observe and what you can say about your observations, okay? So again, chemistry is an empirical science. How do we know anything about anything in empirical sciences? What method do we utilize? Scientific method, right? And what is that based on? Number 1, it's based on what is called observation, right? When I go through all the little facets of the scientific method so you guys understand exactly how it works, and then I'm going to ask you a little question to make sure you got everything I said, okay? All right, so again, it's empirical, it's based on observation. What are other bits and pieces of the scientific methods? We have observation. What else do? We experiment. What do we form? Hypotheses. And then long term, after all this experiment, all these hypotheses, ideally we form laws and theories. And I'll tell you the difference between them in just 1 second, okay? All right, so let's start with just the observation, okay? First step of anything with respect to the scientific method is making an observation, okay? So for example, we utilize this dude right here. Let me get my little pen. This dude right here, whose name is Antoine Lavoisier, to kind of illustrate all the little tenets of the scientific method, okay? So what this dude did, he's a French chemist. He was working in the 1700s. And the observation that he made was when he took, let's say, a piece of wood. So this is my little piece of wood. And he combusted it, so he burned it. So it's on fire. This is the fire. And he did that in a sealed container where no gases, nothing could get out. What he noticed was that the mass of this thing beforehand and the mass afterwards were the exact same, okay? So if you took a log and you burned it, what does it appear to do? Is it there afterwards? No, it appears to go away, okay? That was strange though. If you see something just disappear after it's burning and you measure the mass, it's the exact same as before, what's happening exactly, okay? So this is the observation that he made, okay? All right, so that was his first observation. they also call this the collection of data, okay? What do you think he's going to do after this observation? He makes an observation. What is his next step? Before he can experiment, he has to kind of try to explain that observation, right? So how do you try to explain? What is that called? Hypothesis, right? So next up, he has to form a hypothesis, okay? And so Lavoisier, his hypothesis was built on the fact that he thought that when you burn this wood or you burn whatever you're trying to combust, instead of it just going away, it was combining with something in the air, okay? That was his big hypothesis, okay? So what's really important about a hypothesis is that it's what is called falsifiable, okay? That means it's testable. A hypothesis that's no good, that's not actually a qualified hypothesis, is something that you could never test afterwards, right? If Lavoisier had said, the wood, it just feels like not losing mass, then that's something that we can't actually test, right? But with his hypothesis was that it was combining with something in the air, he can now form more experiments to test that hypothesis, right? And what we mean by falsifiable is if he makes a hypothesis, he tests it, and the experiments that he runs actually go against his hypothesis, then he has to go back and start at the beginning, right? He can't just say, oh, well, I'm just going to ignore that and keep moving. Instead, he goes back, it's falsifiable, it's testable, we have to reevaluate our hypothesis, okay? Okay, so we've got our observation, we've got our hypothesis, now we've made a bunch of experiments to try to explain this, okay? Okay, so then, ideally what's going to happen after you do this is you're going to come across what is called a scientific law, okay? So a scientific law, and I note that I have like erased this. This is what this is talking about. Scientific law is a brief statement that ideally summarizes past observation and predicts future one, okay? So for Lavoisier, his law that he comes up with is called the law of conservation of mass, which states that in a chemical reaction, matter can neither be created or destroyed, okay? That is his law. Note that that summarizes what his observations were. Does it help predict future ones? Right? Could he have, let's say, oh, you know, I'm going to run this experiment, and via my law, it states that I cannot create or destroy matter, so the mass before, the mass after have to be the same. Does that predict future experiments? Yes. Number one, does that explain why? Does the law explain why matter can't be created or destroyed? No, right? So again, it's just a summary, right? Even though we think of laws as being this great thing, really, scientific laws are just kind of more like scientific principles, okay? What's going to help explain why, though? What do we call that? So we have our law, but if we want to explain why we don't lose mass after reactions, what are we going to form? A theory, right? Theories are what explain why we see the things that we do, okay? Again, they're different than laws. So the theory that explains the law of conservation of mass ends up being Dalton's atomic theory, which we will talk about more in the second chapter, okay? Again, laws summarize past observations, theories explain why, okay? Okay, so why don't we call it, instead of a theory, why don't we call it scientific fact? Right? Why do we call it theory? Because theory inherently in the English language kind of says, oh, maybe, I don't know, something like that, right? Why don't we call it scientific fact? So the whole idea why we call it a theory is I would hope a little bit that scientists are mildly humble in the fact that they can figure out that they don't know everything in the world, right? So for example, when Dalton was essentially constructing his atomic theory, all they could do was measure the mass of things, right? That's all they could do. Can we do more technologically wise than measure the mass of things now? So long term, we can even image individual atoms at this point in time, right? He forms his theory based on what he can do at that point in time, but we're going to continue to progress with respect to science and technology, and we don't know, once we get to the next stage, if maybe that's going to open up something that we couldn't have ever thought about when we were Dalton measuring the mass of various things, okay? So that's why it's a theory and not a fact. Okay, are there any questions? No, okay. So let's go ahead and do a Socrative question, okay? So, I don't like this app because it covers things. Do this. So question 1.1, I'll put this up in Socrative. which statement best explains the difference between a law and a theory? And you have 3 possible choices. Again, feel free to talk about this with your neighbor. Oh, is that me? Okay, so if you haven't gotten your answer in yet, please go ahead and do so. Most of you have. Okay, so what is the correct answer here?
B.
B. So B is the correct answer. So A is a law is truth, whereas a theory is mere speculation. No, that's wrong. What's wrong with C? They're switched, right? So this one states a theory describes what nature does, a law describes why nature does it. This would be correct if a theory was why and a law was what. Okay, so those are just backwards at this point in time. All right, good. Most of you guys got that. Okay, so moving on. So I'm just going to take like more minutes of your time. We're going to start, after we talk about scientific method, we're going to start talking about matter and how we can classify matter. So again, what is matter? Has mass and does what? Takes up space, right? So we can classify matter according to 2 different things. Number 1, its state, and we'll talk about what that means. It's physical form. And number 2, its composition. Okay, what makes it up? So what are the 3 physical states of matter? What types of physical forms can matter occupy? So solid is 1. And what else? So solid, liquid, and then gas, right? And those are the ones that we're interested in with respect to chemistry. Okay, so how do these guys differ with respect to one another? With respect to matter. So we'll start with solids, right? Why are solids the way they are? So solids in matter essentially have what is called a fixed structure, right? So they're fixed in space, they can't move at all, and they're also really close with respect to one another, okay? So if you're a solid, you've got a bunch of atoms really close with respect to one another, and you are fixed in your space. You cannot move, okay? So one of the big implications behind that is solids have both what is called a fixed volume and a fixed shape, okay? rigid, fixed shape, can't move with respect to one another. What about liquids? How do liquids differ comparatively to that? Are liquids close together? Little atoms, molecules, are they close together? They're pretty close together, okay? But how do you think a liquid differs from a solid? Do you think that now they can move with respect to one another? Yes, okay? So solids, close together, can't move. Liquids, on the other hand, are still close together, fairly close, but now they can move with respect to one another, okay? The big implication behind that is liquids, when I say solids, liquids have both a fixed volume, right? But now they take on the shape of their container, okay? So solids had a fixed volume, fixed shape. Liquids have a fixed volume, but now they have a shape, whatever the shape is of the container, okay? All right, so then solid, liquid, what about gases? How do you think gases differ? So with liquids, we were moving, so that's good, that's something different, but we were still really close together. What do you think is going to happen with respect to the gases? Are they close together now? No, right? So now, with gas, we're no longer close together, but we're still moving, okay? So because of that, gases take on both the volume as well as the shape of whatever container they're in, okay? And that also makes gases compressible, meaning that you can compress them into smaller volumes. You can't do that for liquids, you can't do that for solids, okay? But solids, liquids, gases, you should know how to categorize each depending on their little properties, okay? All right, so now that was the physical state of matter. Now we're going to classify matter based on its composition, okay? And we have this nice little diagram that's going to help us along in this little process, okay? So we're going to start up here when we're talking about the composition of matter. Let's start up here at the top, okay? The first question that we ask is, does this matter, whatever we're looking at, does it have a variable composition? And I'll explain exactly what I mean by that. If it doesn't, it goes down this way, which is what we call a pure substance. If it does, it goes down this way, it's what we call a mixture, okay? All right, so what is the difference between a pure substance and a mixture? Okay, so number one, a pure substance is made up of only one component and its composition is invariable, okay? Meaning, if I have water, is there anything else in water? No, it's pure, right? And its composition, it's all water, 100% water, right? What is the difference between that and a mixture, right? What if I had something like sweet tea? Is the composition of sweet tea, can it change? If I add more sugar to sweet tea, is that a different composition than what if I had added less sugar to sweet tea? Yes, okay? So if it's a pure substance, it only has one thing, whereas if it's a mixture, it has two or more components to it. And again, we can change the composition of it depending on the mood that we're in that day, okay? Okay, so we've gone down this. So if we are a variable composition, we are a pure substance. We're going to continue down this little pathway, okay? The next question that we ask, is this pure substance, which does not have variable composition, is it separable into simpler substances? Okay, and again, I'll talk about what I mean by that. So, if it isn't separable into simpler substances, it's what we call an element, okay? If it is, it's what we call a compound. And again, I will explain what I mean by that, okay? So, what do we mean by an element? So an element is something that can no longer be broken down into simpler things, okay? An element is something like oxygen. It's something like carbon. You can't break it down and still have that specific element, okay? A compound, on the other hand, is something that can be decomposed into other things. So for example, a compound is something like water, right? So if I take water, we know water is made up of oxygen and hydrogen atoms. If I break that down, can I get something simpler? Yes, I could get just individual oxygens and individual hydrogens, okay? This is what we mean by a compound as opposed to an element. If we were looking at just carbon, can I break down carbon and still have carbon? No, okay? That's what we mean by an element. Okay, so how do we essentially look at various elements and compounds in this book? So a lot of times we use these nice big ball type shapes, these little spherical shapes, right? And with respect to this book, Each element has its own color associated with it, okay? So for example, hydrogen in our book takes on a little white color, oxygen is red, and carbon is gray, okay? Just note that whenever we're looking at this, we're looking at these as respect to individual atoms. So for example, this guy, how many oxygen atoms are there? How many little balls are there? 2, okay? What about this? What is this guy in the middle? This is an oxygen, and the 2 white ones are what? Hydrogens, okay? So on and so forth. Okay, so how many elements are there? There's a lot, right? So where do we see them? Where do we find them? In our textbook or on the wall, etc.? Periodic table. It gives us all of our elements. There are currently 118 named elements. How many of those actually occur naturally, though? So 91. There are only 91 naturally occurring elements. The remainder we have synthesized in a laboratory, okay? So note, we have 2 different little pie charts here. We've got the composition of Earth's crust as well as the composition of the human body, okay? So of those 118 that are possible with respect to elements, 5 of them make up 90% of the Earth's crust, of the Earth by mass, okay? So lots of different elements, but only 5 really actually contribute to the composition of Earth. What about the human body? So 3 of them make up 90% of the human body, which is the big element that is kind of heavily in both of these, the Earth's crust as well as the human body. Oxygen, right? So oxygen, really prevalent in Earth's crust as well as the human body, okay? Okay, so I'll go ahead and stop there, give you guys a break for the first day, and I don't know what all these people are coming in so early, but we will start back up talking about the various chemical symbols of the elements on Tuesday. Getting to start recording. Okay, so now I'm recording, so I apologize for that. Okay, so that is our elements. That's how we represent them. We'll talk more about our elements in chapter 2, what they are made up of, etc. Okay, so now pure substances. We've already talked about elements. Now we're going to talk about compounds. Okay, and so the big differentiation between an element and a compound was the question, can it be broken down into simpler things? Okay, a compound is a pure substance that can be broken down into simpler things. An example of that would be water. So water is a pure substance as long as you have pure water, nothing else in it. When we break down water, though, what do we get? If we break those little lines that connect the H and the O's, we get oxygen and we get hydrogen. Okay, those are 2 elements that compose water. When we break down water, we get simpler things. Because of that, this is a compound. Okay, so now there's one little distinction that I need to make. What separates this, a compound, from a mixture? All right, so a mixture could be, let's say we had a mixture of hydrogen and oxygen, and I put in, let's say, 25% hydrogen and 50, or I guess I need to add up to 100, 75% oxygen. This is a mixture of hydrogen and oxygen. The difference between this and our compound water is the fact that when we break down water, we're always going to get 1 oxygen for every 2 hydrogens, okay? So that's what's called the law of constant composition, and we'll talk again about that next chapter, but just note that a compound is always going to be broken down into the same exact ratio, whereas a mixture, you can make up however you want. It can be 50% and 50%, 25, 75, etc. Okay? Again, we're dealing with compounds. These are our pure substances. Okay? Okay, so moving on. Now we're going to go down the other little route, right? So we just talked about all of these guys, okay? Now we're going to go back to our little matter, and we're going to say, all right, does it have variable composition? If it does, it is what we call a mixture, okay? Now from here, the question is it uniform throughout? And I'll try to illustrate what I mean by that, okay? All right, so dealing with mixtures, a couple things to note. A mixture that is uniform throughout is something that we call a homogeneous mixture, okay? A good example of this would be something like tomato soup. So tomato soup. Make sure I spelled that correctly. Okay, so tomato soup. When you look at it and you take your spoon to go and eat it, number one, it's a mixture. There's a lot of things that are going in there. You can add more salt if you want. You can vary the composition of everything. Number two, if you take a little bit of tomato soup off the top and you take a little bit off the bottom, is it different? So it shouldn't be, right? So the whole idea behind what is called a homogeneous mixture is the fact that it is not variable throughout. If you take a little bit here, if you take a little bit here, if you take a little bit here, they're all going to be the exact same components, okay? Now contrast that with something like beef stew. All right, so beef stew is a mixture. There's a lot of stuff that goes in there. Again, you can vary that however you want. With beef stew, if you take a little bit right next to like a piece of carrot and you take a little bit right next to a piece of potato, are they going to be different? Yes, right? Because it's different. There's different chunks. There's different layers. There's different like stratifications of that, okay? So this guy, tomato soup, even, uniform throughout, that's a homogeneous mixture. Something like beef stew is not uniform throughout. There's bits and pieces of different things everywhere. This is what we call a heterogeneous mixture, okay? So homogeneous mixtures, uniform throughout. Heterogeneous mixtures are not uniform throughout. Another example of a heterogeneous mixture would be something like, let's say, sand water, right? If you put sand in a cup of water, what happens to it? Did it float? It's nice and happy? No. So sand will just sink to the bottom, right? So we've got water up top, and we've got sand down below. This, again, is a heterogeneous mixture, right? If I took a little bit from here, right down here at the bottom, it's going to be different than if I took a little bit from up at the top, right? Because, again, they have not evenly dissolved. It's heterogeneous because it's variable composition throughout, okay? All right, so a couple more things. Another thing that we call at least a homogeneous mixture, still don't know how to use this, we call this guy a solution, okay? So our tomato soup, in theory, was probably not the best example, but a homogeneous mixture is also called a solution. This little guy right here, the blue colors, this is a homogeneous mixture. Again, it's uniform throughout. This is what we would call a solution, okay? All right, so our mixtures. We've talked about our two different types, heterogeneous mixtures and homogeneous mixtures. So now we're going to talk about what happens if we have a mixture and we actually want to separate the components of that mixture from one another, okay? So there are three different techniques that allow us to do that, to separate the components of a mixture from one another, depending on what type of mixture we're dealing with. We're going to go through each individual one separately, okay? So they're called filtration, this is distillation, and this is chromatography, okay? Okay, separating the components of a mixture. So, first thing we're going to say is filtration. Filtration is a means by which we can separate a heterogeneous mixture, okay? A good example of this, again, goes back to not my failed beef stew analogy, but instead the nice little sand water mixture that we had. This was, again, a heterogeneous mixture. We had sand at the bottom and we had water at the top. I want to separate these two components. What would be the easiest possible way for me to do this? I've got a solid sitting at the bottom and a liquid at the top. I want to remove the two from one another. How could you possibly think of just easily removing the two? So if you were very, very, very careful, you could potentially just pour off the liquid and, trying not to disturb the solid, just pour off the liquid into a separate beaker, okay? This process, this gentle pouring off, is something that is called decanting. It's a fancy word for just gently pouring away liquid, okay? Chemistry likes to do this, give fancy words to very simple things. A more precise way, though, would be through this method called filtration, Okay, so in filtration, we will have our mixture. Again, this is a heterogeneous mixture, so usually this is good for separating a solid from a liquid, okay? And what we'll do is we'll set up something that is called a funnel. So this guy is a nice little funnel, and in that funnel we will put something that is called filter paper, okay? So filter paper, okay? This is very similar to a coffee filter, okay? So we have our little sand water mixture here, and I pour it through a solid paper. What's going to stick to the paper? Sand, right? So the sand is going to end up top. What's going to go through? The water, right? So again, if I wanted to be very, very, very precise and careful about separating my solid from my liquid, I could use this method of filtration. I would need a filter paper, and I would go forward from there, okay? Have you guys started the lab yet? Has anyone taken a lab course yet? No? What days do they start at? Tomorrow, okay. I don't think you do this yet, but I think you will as the semester moves on. Filtration is lots and lots of fun. Okay, so that's how to separate a heterogeneous mixture. What if we had a homogeneous mixture? What if we had a mixture that consisted of two separate types of liquid, okay? So let's say we have a mixture of ethanol, which is another word for just alcohol, and we'll go back to our simple water, okay? So again, when you mix ethanol and water, do they mix evenly? Yes, they do. So you guys are all very young, so you probably wouldn't know. But ethanol is just, again, another word for the alcohol that people drink. And so, like an ethanol water mixture would be something just like vodka, right? When you look at a bottle of vodka, which you never have, your parents have had it, something like that, right? Is it evenly distributed? Can you tell the difference between how much ethanol and how much water is there? No, right? So it is uniform throughout. So this is a homogeneous mixture, okay? All right, so this is what we have. This is what we have, our mixture of ethanol and water. We want to remove the ethanol from the water. How would we do that, okay? So this is when we utilize a technique called distillation. So what's going to happen in distillation is you're going to have your little mixture in your distilling flask, okay? So this is our ethanol water mixture. And what you're going to do to that distilling flask is you're going to heat it, right? So we set this little guy on fire. It's heating, okay? And what we're going to take advantage of here are the two different boiling points between ethanol and water, okay? So ethanol has a lower boiling point than water. That's an important thing to note, okay? What is boiling again? It's going from a liquid to a gas, okay? So that's what we're trying to take advantage of. So as we start to heat our mixture, because ethanol has a lower boiling point, it's going to start to transfer between a liquid to a gas first, right? It's going to start to boil first. So what's going to happen is this guy, moving from a gas, is going to essentially come up through the neck of the flask, right? And again, these are all little ethanol molecules, okay? As this continues to occur, it's going to encounter this little thing called the sidearm. And what the sidearm is doing is giving it an opening for which it can come down to this thing called a condenser, okay? And what happens in a condenser is the gas is in this inner tube, and on this outer tube, we have very cold water that's circulating around that inner tube, okay? What's that going to do to the temperature of that inner tube if we had cold water that's essentially just circulating along the outside? It's going to decrease it, right? So if it's a gas, if the ethanol is a gas up here, and it starts to come down this condenser, and it's going to cool down, what do you think is going to happen to it? It's going to recondense, so it's going to go back from a gas to a liquid, okay? So that is the importance of this condensing tube. As it goes back from a gas to a liquid, notice that this is slightly slanted, right? So what's going to do because of that? So it's turning into a liquid here. Is it just going to stay there? No, because of that slant, it's going to continue to go down because of the force of gravity, where it goes down into this fat flask and collects, okay? So again, as we continue to do this, the ethanol has moved in, it's become a gas, it's recondensed in the condensing arm, and it's fallen into our collection flask. What's going to be mainly in here at this point in time? Just ethanol. And then what's going to be left over from our mixture? Just water. Okay? So again, this is distillation, this is the technique, and it's a means by which you can separate a homogeneous 2-liquid or 3-liquid mixture. Okay? And it's used very frequently to separate water from ethanol. Okay, so one more. I think they kind of knock it over the head with the chromatography. So we looked at filtration. That was a means of separating a heterogeneous mixture. We looked at distillation, a means by which you can separate a homogeneous mixture. Chromatography is another means by which you can separate a homogeneous mixture. Homogeneous mixture. Okay? And what this is going to take advantage of is differing affinities for certain molecules for solid substances. Okay? So what happens? So we're looking at differences in affinities for solids. Okay? So what's going to happen is we have what is called our chromatography column. Okay? And again, this is kind of packed with this like sand type structure. Okay? So imagine it just being kind of like the solid matrix where liquids can go through. Okay? We're going to pour our mixture down this column. Okay? And depending on the affinities for the things in that mixture for that solid substance depends on how much they actually want to stay with the solid. Okay? So for example, things that have a very, very high affinity for whatever's in that solid phase will stay at the very top of the column. So these guys have very high affinities. Whereas things that have very low affinities, don't really like to participate with the column at all, will essentially move very quickly down the column. Okay? Things that are in the middle kind of stay in the middle. Okay? So again, for this technique, we are taking advantage of differing in affinities for various things, and on the basis of their affinity, they will move either very quickly or very slowly down the column. This is frequently used to separate dyes in either little crayon markers or dyes in wool or dyes in various things. Okay? I'm not super into chromatography. I don't really know why they throw it in this textbook. Okay, all right. So those are the various ways that we can separate mixtures. Okay? We talked about mixtures. We talked about what separation means. What all of these techniques took advantage of was differences in physical and chemical properties between the components of a mixture. Okay? But what is a physical property? What's the difference between a physical property or a chemical property? So ideally, you guys should know that. That's what we're actually going to talk about next. But that distillation, that chromatography, that filtration, what we were taking advantage of was differences in physical and chemical properties. Okay? All right, so what is a physical property? So a physical property of matter is something that you can observe without actually changing the substance. Okay? So for example, when we took liquid water and we turned it into gaseous water, do we change water at all? No. As a liquid, what was happening with respect to the molecules? They were just kind of close packed. They were moving with respect to one another. When we heated it and turned it into a gas, what happened to them? They just got farther away from one another. They still stayed the exact same chemical as water. Okay? So this is a physical property. Again, if we're going from a liquid to a gas, what is this called? This is boiling, and the property is boiling point, right? Again, it's something that you observe without actually changing the component or the chemical substance of the thing. There are a lot of other physical properties. So another one would be melting point. Melting point is just going from a solid to a liquid. Others are things like density, hardness, color, and odor. Okay? Again, these are things that are observed without actually changing the substance into another substance. Okay, so if those are physical properties, what do you think chemical properties are going to be? So these guys weren't changing it into another substance. What do you think is going to happen with chemical properties? They're going to be things that you observe by doing what? changing something into another substance, okay? Okay, so what's a nice example of a chemical property? So let's say we took hydrogen gas and we combined it with oxygen gas, right? And we just kind of provided just a little bit of a spark. What's going to happen? Hydrogen, oxygen, how does the rockets, how do they get up into the space? So this exact same reaction, right? So hydrogen is super flammable. If you combine it with oxygen, it's going to explode, okay? But in the process, by doing that big combustion, it forms a new substance. It forms water, okay? So again, they combusted, we got this big explosion, and we made something new in the process. So this would be called, a chemical property would be called something like flammability. By observing it, you've made something new. Okay, so we observed it with hydrogen and oxygen, we made water in the process. Same thing with iron, nails, right? So we have nails, and they are not galvanized, so it's just pure iron, and you left it out in the world, what would happen to it? It would rust, right? That type of property would be called corrosiveness, I would say. And what's happened is you've taken iron, it's a nice pretty iron, Fe, and you've actually made a new chemical substance. You've made what is called iron oxide. Okay, so you've combined iron with oxygen, you made a new thing, we call it rust, but again, you're observing this by changing one compound into something completely different. Okay, and again, we would call this as a property corrosiveness. Corrosiveness. It's going to let you know I can't spell. So when I say it out loud, hopefully you can spell and you can write that down. Okay, a couple more, and then we're going to take a little questionnaire. When we see these properties, right, they are usually accompanied by some sort of change, right? So if you have a physical property, it's going to usually correspond to a physical change. Oh, wait, did I say chemical? If you have a physical property, it's usually going to come along with a physical change, whereas if you have a chemical property, it's going to come along with a chemical change. So a physical change would include things like changing the temperature of a substance, right? Again, you don't change the compound when you change the temperature, changing the volume or changing the state. Chemical changes are going to be things like oxidation, combustion, and decomposition. Okay, so hit the nail over the head. One thing to note about chemical changes, and this is kind of important, is the fact that very frequently a chemical change will be associated with some sort of telltale physical thing, okay? So for example, if we took a penny, so this is our nice little penny, and made kind of primarily of copper, okay, so many pennies are some sort of mixture of copper, and we reacted this with a very strong acid, okay, so very strong acid. The penny would seem to essentially just kind of dissolve away, right? In the process, we would evolve a gas that was brown, a brownish gas, and what is the color of the solution turning? Blue, right? So again, color is a physical property. Chemical changes usually are accompanied by some sort of physical property like color to tell us that something is actually changing, okay? Just want to note that very quickly. Okay, so let's go ahead and do a Socrative question. So I have 4 different changes, and I want to know, are these changes physical or chemical? And then there's a second part to the question, but you don't have to answer that. You only have to answer the first part. So physical change or chemical change. And I'll go ahead and post that. 1.2. Quiz. Just as a reminder, the room number or the room name is Macintosh 113. Let's go ahead and get your answers in. We'll go over these. Okay. So most of you guys did really well on these until like the last two, I think, ish. So, number 1, chemical or a physical change. A copper wire is hammered flat. Is this physical or chemical? So this is physical. Again, we don't change copper. We just kind of we just hammer it. This hammering things, what kind of property is this? I didn't really go over this one, but this is, I'm just going to say, this is called the malleability. Malleability. So malleability is like how much you can mold a certain solid, right? So most metals are actually fairly malleable. You can bend them, you can hammer them fairly easily. All right, so what about nickel dissolving in acid? Is this physical or chemical? So this is chemical. Again, we use the color change because it turns blue-green to kind of denote that there is a chemical change occurring. And so what would this be as a, like the actual property? This is kind of like corrosiveness. Again, what I'm referring to is this last section. What type of property is demonstrated in each case? So the first one was malleability. The second one is corrosiveness of the acid. What about dry ice subliming without melting? So what is sublimation? This is going from a solid, but instead of going through the liquid phase, what does it pass directly into? Gas, right? So what is dry ice? This is just CO2, right? So CO2 solid, nice and cold, and it immediately goes into the gas phase. That is what subliming is. So is this physical or chemical because of that? This is physical. I don't even know what you would call that as a property. Sublimation point, maybe, something like that. We'll just leave it like that. And then number 4, a match ignites when struck on a flint. Is this physical or chemical? This is chemical. Again, this would be something like flammability. And we're changing the actual structure of the match, right? When we strike a match on a flint, it burns. What happens to it? Just turns into some component of the air, okay? So we've actually changed the match. Okay, so we'll do another one. I like this one. So I guess, yeah, it's all of our left. So to our left, we have a bunch of liquid water molecules. So these guys are liquid. And I want to know which picture accurately describes what happens after they've gone from a liquid to the gas, okay, after they've been vaporized. So is it A, B, C, or D? What is this? 1.3. So please feel free to discuss it with your neighbor too. Okay, so go ahead and get your answers in. Okay, so what is the correct answer here? We have A, B, C, and there's no D. So A, B, or C? A, right? So again, boiling is a physical property. It's something that you observe without actually changing the compound, right? We have water, which is oxygen, hydrogen, and hydrogen. It's close together when it's a liquid, right? That was kind of our big thing. As we turn it into a gas, it's still going to be oxygen, hydrogen, and hydrogen, which is now what has happened. They've just gotten farther away from one another, okay? So the correct answer is A. That's good. Most people got that correct. Okay, so moving forward, that's kind of the end of talking about matter in this chapter, okay? Again, we'll come back to matter in chapter 2, but the end of this chapter deals with making measurements, which is very central to the study of chemistry, okay? All right, so again, chemistry is an empirical science, meaning we make observations, we make hypotheses, and then what do we do to either prove or disprove our hypothesis? We experiment, right? And so experimentation usually in some way means we're measuring things, okay? So we're going to talk about all of these various things you guys have to be aware of when we're actually making measurements. We're going to start by talking about units, okay? And I'll try to illustrate why units are kind of important with respect to making measurements. So units are essentially just going to be standard quantities that allow us to compare measurements from one scientist to measurements from another scientist, right? And so we have defined these standard quantities, and we're going to go through all of the units that we will use in chemistry or in science in general, okay? There are two common unit systems, one that we use and the one that the rest of the world uses, okay? So we use, in America, the English system, unfortunately, all right? So English system, what type of units are those? If I'm measuring the length of things, how do I usually measure that? Feet, inches, etc. What about the weight of something? Pounds, right? Nobody else measures in pounds. And we'll talk about pounds in a second, how it's not actually a measure of mass. Everyone else uses the metric system, okay? And we're going to go through kind of the common units of the metric system, as well as how they fit into overall science and chemistry and how we actually measure things, okay? So why is this important? Why is distinguishing between the English and the metric system important? So a good example of this happened in 1999, okay, a very long time ago at this point in time, which is kind of sad. But 1999, NASA launches what is called the Mars Climate Orbiter, okay? The whole idea behind this guy is that it's supposed to go up, shoot it up to Mars, it get to Mars, and sit there and orbit Mars, and essentially just record details about its climate, okay? It's going to be very, very, very informative. The problem was, when it got there, instead of going into orbit around Mars, it crashed into the surface, okay? So this is like millions upon millions of dollars that are just wasted lying on the surface of Mars. When they get back, and they're like, oh, what happened? They do this little investigation, and they find that the reason why it crashed is because somebody forgot to convert English units into the metric system, okay? So it was a misplacement of units. That's why it got too close to the surface of Mars, and that's why it crashed into the surface, okay? So this is a good example of why units are important even if you don't care about them yourself, okay? All right, so let's start upon our journey into how we measure things with respect to units. So I said most people use the metric system. Science uses what is called the International System of Units, or what we abbreviate as the SI. This is essentially a derivative of the metric system, so we'll use very common units, but they differ in certain ways, and I'll try to illustrate where they differ as I go through them. The ones that we're going to focus on right now, the units that we're going to focus on, are length, mass, temperature, and time. And we will talk about these other guys, these other SI base units, at some future time in this semester. Okay, so let's go by starting to talk about how we measure length in the SI system. So the base measurement of length is what is called a meter. You guys are probably fairly familiar with a meter, right? So a meter is approximately-ish a yard. What is a yard in our normal English system? 3 feet, right? So 3 feet is approximately equal to 1 meter. That's just going to give you an idea of the magnitude of these things that we're dealing with, right? How many feet are in a football field? Or no, wrong one. How many yards are in a football field? 100, that's easy. So 100 yards is approximately equal to 100 meters, okay? It's a little bit off, give or take, but just think 100 yards, that's about 100 meters. All right, so all of these units have really very precise measurements, going back again to the SI system. I'm not going to go through these, but just note, well, I will do this one, that 1 meter is actually precisely defined as 1/10,000,000th of the distance from the equator to the North Pole going directly through Paris. Okay, so this is what I mean by all of these being very precisely defined. You do not need to know that, okay? Okay, so that's the meter. Second is how we measure mass in the SI system, okay? So thinking about the metric system, how would you say you would measure mass of something? Grams, right? So if I was just like, oh, metric, I measure in grams, it's close, but actually the base unit for the SI system of measurement is the kilogram, okay? So a kilogram, 1 kilogram is equal to 1,000 grams. That's kind of like the unit conversion between those two, okay? A kilogram is equal, if we're converting, and these are some things that you may want to note for your homework, is equal to 2.205 pounds. So that's the conversion between kilograms and pounds. But what's the problem with trying to convert those two? A kilogram is a unit of mass, which is essentially a unit of how much stuff there is in something. What is a pound? Yes, yes.
Pound is a measurement of weight, and weight is a measurement of force. On a body that's, for example, a pound. If you were to take the mass that would be required to create a pound of force on Earth wouldn't be the same on a different planet that's a different size. So it's more so just a measurement of force exerted by overall gravitational pull.
Yes, very good, right? So weight is a measurement of force, again, because of the gravitational pull of Earth, okay? Mass is actually how much stuff is in something. It doesn't actually depend on what gravitational field we're actually living in. It's all going to have the same amount of mass. So that's why SI goes back to mass, okay? Again, there is a very specific measurement of how they got what a kilogram is, but we're not going to talk about it. Okay, so then the third base unit in the SI system is our unit for time. This is the actual only one that conserves to the English system, right? So how do we measure time here? Hours and seconds. So same thing with respect to the SI system. Our base unit for time is the second, okay? And again, you can read these nice little definitions for them. Just note that the human heart beats once every second, and the age of the universe is approximated to be 4 × 10⁻17 seconds, which is a very, very, very long time. Okay, gosh, is that it? I think that's almost. One more, temperature. Okay, so temperature is a measure of how much energy, thermal energy, is in a sample of matter. Okay, and we will talk about what temperature comes from and how we get it later on in the semester. For the English system, how do we measure temperature? Fahrenheit, right? And most importantly, it is a degree Fahrenheit, okay? Does anyone else use Fahrenheit? No, right? Most other people use what? Degrees Celsius, okay? And again, it is a degree. I do not care about the conversion between these two, right? Everything that I will give you on any exam ever, I will never give you Fahrenheit. I will only give you Celsius, right? Again, this is a good example of metric. This is the metric unit for temperature. The SI unit for temperature, though, is what is called the Kelvin, which comes from the absolute scale, okay? So for a Kelvin, it's not a degree Kelvin, it is just a big capital K, okay? So degree Kelvin would be incorrect. The conversion between the Celsius and the Kelvin, So Kelvin is equal to degrees Celsius plus a certain number. What is that number? 273. And technically I think it's 273.15. I don't care. It's 273. So if I had a 25 degrees Celsius day, how many kelvins would that be? 273 plus 25 kelvins would be 298 Kelvin. Okay? Okay, so temperature, I've already said, is a measure of the amount of energy a sample of matter has, but it also determines the transfer of energy, right? So if I had a hot cup and I put my hand on it, where would that hot go to? Right? So if we have something that's hot and we put something that's cold to it, does more heat go into the hot thing, or does heat leave the hot thing and go to the cold thing? Heat leaves the hot thing and goes to the cold, right? So temperature allows us to determine how thermal energy is going to be transferred. If something has a very high temperature, it is going to transfer to things that have low temperatures. Hot always transfers to cold. That was a bad analogy for me to try to do. Okay, so those are the basics of SI. So now, really quickly, again, we're going to continue on in this measurement thing. We're going to talk about something called prefix multipliers, okay? So frequently in science, in chemistry, etc., we will make measurements that are either really, really, really tiny or very, very, very large, okay? So for example, the diameter of a hydrogen atom ends up being this number, okay? This is a hassle to make sure and count out all of these zeros, etc. What would be a better way to represent this number that's a little bit easier to write and a little bit clearer on what we're actually trying to represent? Scientific notation, right? So one way to make these small numbers and these big numbers easy is to utilize scientific notation. So when I do that, for this tiny number, this diameter of hydrogen, I'm going to count how many times it takes me to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to right to the right of our first non-zero number. Okay, so I've gone 10 spaces to the right. So a way to write this in scientific notation would be 1.6 times 10 to the minus 10th. And then what is my unit here? Meter. It's a unit of length. Okay. So when we move the decimal to the right, what happens to the sign on the exponent? Gives us a negative sign. Okay. What about a big number? What about this guy? If I wanted to write this with scientific notation, I would count again how many decimal places. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3, 4, 5. It takes me to get to the last non-zero number, right? And so now I would write this as 1.234 times 10 to the 9th. There is no unit, so I leave it unitless, okay? I went to the left here. What's the sign of my exponent? So this is left, moving the decimal, and we get a positive exponent because of that, okay? So this is nice. This is easy. Stick with me. We're almost there. Again, though, this can kind of be a hassle, right? Having to write this 10 to the minus 10 or 10 to the 9th. There's another way that we can make this even easier, right? We can use what are called prefix multipliers, okay? So, for example, let's say I had this volume, okay? And again, I don't want to write the zeros, so I'm going to go ahead and convert this to scientific notation. So when I do, I get 4.56 times 10 to the what? We get 1, 2, 3. So 10 to the minus 3 liters. So I'm super lazy, and I don't want to write that 10 to the minus 3 every time. So this would be helpful if I had some sort of prefix multiplier that meant 10 to the minus 3 of whatever unit I was using, right? And this is kind of the purpose of all of these prefix multipliers. So if I go on my little chart here, I find that the milli with the little lowercase m represents this 10 to the minus 3, right? So instead of putting this, another way to represent this would be 4.56. And again, because I don't want to write the 10 to the minus 3 milliliters. Okay, so this is our prefix multiplier. And again, it indicates that this is 10 to the minus 3. this is a big chart, right? There are a lot of little multipliers that are on here, so I'm going to let you know which ones are going to be important for you moving on to know the conversion for, okay? So milli is 1, okay? This guy, micro, so can you guys see that? No, not really. So micro, the name micro is represented by the Greek letter mu. Unfortunately, in Socrative and a lot of other things, I don't have that mu capable. So frequently, if I mean micro, I will just write micro sometimes. But this guy represents 10 to the minus 6. You should know what the nano is. This is just a lowercase n. This represents 10 to the minus 9th. You should know what pico is. This is 10 to the minus 12th. And then you should also know what the kilo or the kilo is, okay? So this is 10 to the 3rd. This is big stuff, okay? Just note that the base unit goes right here. So everything that is smaller goes down, and everything that is larger goes up from the base unit. Okay, so it's important to note too that when you're using prefix multipliers, you always want to pick the one that is closest to the size of the thing that you're measuring, right? For this guy, that 10 to the minus 3 told me I need to use milli. Would it have been appropriate for me to try to have converted that to micro or to nano? No, because then it would be this gigantic number, right? It's not appropriate. So you always want to pick whatever this is as close to this as possible, okay? Okay, so I want you to go ahead and try that on your own. So I have a number here, and I want you to tell me what prefix multiplier is appropriate for converting that number and reporting it. All right, so go ahead and get your answers in. We have another one right after this. So actually, I don't remember what I represented the letters as. What was the correct answer here? D was right, but what does that represent? Micro. Okay. So with respect to this guy, what would I first do to try to figure this out? I would probably convert to scientific notation. So if I did that, I would get 5.57 times 10 to the minus fifth, right? And so what is micro? Micro is 10 to the minus 6, whereas milli is 10 to the minus 3. So this guy, 10 to the minus 5, is closest to this. So micro would be the best one. What would it be converted to micrometers? 55.7 micrometers. And again, to do that, if I'd just gone one more here, this would have been 55.7 times 10 to the minus 6 meters. And then we could just directly replace the micro with the 10 to the minus 6, okay? Now, one more. You're actually going to convert. So I want you to convert between different prefix multipliers. So, and I don't actually know how I pose this either, so you may actually have to type in a number. But I want to know, number one, how many milligrams are in 0.134 grams, and then how many meters are in 1,340 micrometers. So we'll see how I actually put this in. Oh, yeah. long as you're happy with your answer. Okay, so let's go ahead and go over these. I should note at this point in time that with Socrative, especially in the short answer type questions where you guys have to type in something, I can either like not have there be a correct answer and just see what you guys say, or I can actually write a correct answer and then it could tell you, yeah, you're correct. But again, there's so many ways because like people won't put zeros in front of decimals, or they're like not put a space in between milligram and gram. So if you wrote it right and you're good, you got the right answer, you're fine. I just put some of those in there so that if you wrote it in the correct format, it would tell you, you'd get a green thing and you'd be happy with that, okay? So let's go ahead and do the first one where we're converting our 0.134 grams to milligrams. All right, again, the milli, so little lowercase m, is, what is that prefix multiplier? 10 to the minus 3, okay? So a couple things to note. We're going to talk a little bit more about this when we talk about dimensional analysis, but a lot of times when I convert things, I like to use this little railroad track notation where my given is on top, okay? And what I'm going to use on bottom is my conversion from my given to the thing on top. Wait, thing on bottom is conversion from my given to the thing I want on top. I'll try to explain what I mean by that, okay? So if I have a gram on the top of my little railroad track, if I want to cancel gram, what has to go on the bottom? Grams, right? So all of these little units, we're going to act like they're just like algebraic quantities. So I want to get rid of the gram, I have to divide by the conversion from the gram. And what am I going to? Milligrams, okay? So now the question is, what is the conversion between gram and milligram? There are two ways to look at this, or three. I don't know how many fingers I have up. So one is, there are, in 1 gram, how many milligrams are there? So the conversion here is 1,000. The milligram is smaller, right? That 10 to the 3 represents 1,000, right? So in 1 gram, I get 1,000 milligrams. Another way to look at that is using the prefix multiplier directly, right? If I had 1 milligram, how many grams do I have? 10 to the minus 3 grams. Whichever one you want to use, it doesn't matter because you're going to get the exact same answer, right? So for me, I always like this one for some reason, but please use the one on bottom as a unit conversion if you want, okay? So again, this is my statement of equivalency. For every 1 gram, how many milligrams do I get? 1,000. So if I take this number and I multiply by 1,000, I get 134. And again, these guys cancel, and I'm left with this. This is similar. Multiplying by 1,000 is the exact same thing as dividing by 10 to the minus 3, okay? All right, so then on bottom, this guy, I've got micrometers. I want to convert to meters, okay? So again, what is the number that's referring to micro? So in 1 meter, how many micrometers do I get? So 10 to the 6 micrometers go into 1 meter, or I have 1 micrometer. How many meters do I have? 10 to the minus 6 meter. Okay, again, both of these are equivalent to one another. It's just whichever one you want to use is up to you. Okay, so my micrometer is on bottom. So if I, wrong one. So if I divide by 10 to the 6 micrometers for every 1 meter, if I use this guy, that gives me what for my answer in terms of meters? 0.01340 micrometer. Oh, no, we're in meters. My bad. 0 meters. Micros cancel. This is the same thing. 1,340 micrometers is equal to 0.00134 meters. We'll get lots of practice doing this. Don't you worry if things did not go your way with respect to this conversion, okay? All right, so we have like maybe 4 minutes left, 5 minutes left. We'll go ahead, no, okay, yeah, we'll go ahead and stop here, okay? So on Thursday, I am going to start by talking about significant figures. I'm going to spend the first 40 minutes-ish talking about that, and then we will do the activity for the remaining amount of time. Let's say I wanted to measure something like the volume of a substance, okay? Is volume included in any of my base units? No, right? But what is a volume? If you wanted to measure the volume of a cube, how would you do that? You would measure what with respect to a side? The length, right? So the length with respect to a side, if you wanted the volume of a cube, though, what would you have to do with that length? You would have to length times length times length. That's how you get the volume. So volume is just the length cube, especially with respect to a cube, right? So what is our base unit with respect to length? A meter. So if I wanted to measure the volume of something with respect to our base units and the SI units, this would be a meter cubed, okay? So this is what we call a derived unit. It's a combination of other units that essentially gets us whatever quantity we're measuring, okay? Now think about the length of a meter. How big is a meter again? It's about a yard, right? What would be a yard cube? How large of a volume would that be? Very large, right? Do you think you're ever going to measure a meter cubed with respect to volume in the lab ever? No, right? So a more useful quantity is what is called the decimeter cubed. So deci with respect to a meter is just a tenth of a meter. So a decimeter cubed is defined as a liter. Does everyone have a good idea of what a liter is? What kind of magnitude of volume it is? So do you think you'll ever be measuring anything with respect to a liter in the lab? Probably not, right? So if we go down just one more order of magnitude, the milliliter, which is what you'll actually probably be measuring quite a bit of, is defined as a centimeter cubed, okay? So centimeter cubed is equal to 1 milliliter. And again, this kind of gives you an idea of the size and scope of each of these things, okay? What is a milliliter compared to a liter, just to bring back those prefix multipliers? So 1 liter, what does that milli prefix indicate? Right, 1/1000. So there would be 1,000 milliliters in 1 liter, or 1 milliliter is a thousandth of a liter, okay? So we will use these prefix even though we're not actually going with the base units necessarily. All right, so this is the wrong slide. Get to sig figs, we do have to briefly talk about one other little thing. So last time, what did we end with? What were we talking about? Talking about units, right? And so we had a bunch of base units with respect to the SI system of units. So what was our base unit with respect to measuring the length of something? This was meters, right? What about the mass of something? What was our base unit? Kilograms with respect to SI. Time was seconds, right? And temperature, what was temperature? Kelvin, okay? So those are the base units, right? But let's say I wanted to measure something like a volume of a substance, right? So actually, derived unit would be something like the density of a substance, right? So what is density defined as? Density is mass divided by volume, right? So our base unit for mass, what is that again? It's kilograms. And then our volume technically is a meter cubed. But frequently, instead of using this kilogram per meter cubed, we will be measuring density in terms of grams per centimeter cubed, as well as grams per mil, because again, 1 centimeter cubed is equal to 1 milliliter. Okay, so when we measure density of stuff, we usually do it in grams per milliliter, okay? All right, so with respect to density, this again is another derived unit. This is something that we call an intensive property, okay? An intensive property is a property that does not depend on the amount of substance that is there, okay? So for example, if you had some little nugget of gold and it was 5 grams, right? And then you had another nugget of gold that was 100 grams, would the density be different between these two? No, the density doesn't change. It's intensive. It does not matter how much stuff you actually have, the density remains the same regardless, okay? So because of that, intensive properties, things like density, boiling point, color, these are usually utilized to identify a substance. No matter how much substance you have, the density is always going to be the same. If you can measure that, then you can usually identify what the thing is. Okay, in contrast to intensive properties, there are also things that are called extensive properties. So extensive is this guy. This is going to be a property that actually does depend on how much stuff you have. Okay, so something like that would be mass. If you have 5 grams versus 100, that's extensive. It does depend on how much you have. Same thing for volume as well as energy. Okay, and we'll come back to this idea behind intensive versus extensive in like chapter 5, I think. Okay, so that's kind of like the basis behind the unit. We're now going to start talking about significant figures, which is kind of like the main thing that you should be taking away from this chapter. And that's why I tried to do activities, etc., have lots of homework questions with respect to significant figures, because it's important and we'll utilize it throughout the entire semester. Okay? So who has heard of sig figs before? Quite a few people. Okay? So what is the entire purpose of significant figures? You don't have to answer, but just note that in chemistry, we make a lot of measurements, right? And the measurements that we make and the certainty with respect to the measurements that we make depend on the instrument that we're using to make the measurements with, okay? We cannot improperly report a bunch of certainty with an instrument that doesn't have a lot of certainty, okay? So we have to essentially convey how certain we are with respect to the instrument that we are using. To preserve this certainty, when we actually utilize these numbers for calculations, this is why we use things called sig figs. And again, I'll try to explain what I mean by that in a second. Okay, so what do I mean by certainty with respect to instruments? Okay, so let's imagine that you have 2 different groups of scientists, okay, and they're both going out trying to measure the concentration of CO, so carbon monoxide, in the atmosphere, okay? And so one group, we'll say these guys are group number 1. They go out and they measure the concentration of carbon monoxide every 5 years for like 20 years, okay? And so they denote it like this, and this is the instrument they are using. It gives them that amount of precision, okay? Let's say group number 2 goes out, measures the exact same thing, but they use a different instrument, right? And when they use their instrument, this is the recording that they get in parts per million. Which of these 2 groups has a more precise instrument? The group on the left or the group on the right? Or I guess you're left and right. Yeah, left and right. Okay. So group 1 or group 2? Who's got more certainty in their measurement? Group 1. Why do you think that? Because of the decimal point, right? They report their measurements to which place? The 10th place, right? What about these guys? What can they report it to? Just the ones, right? So this is what I mean by essentially conveying our certainty in measurement. In science, when we make measurements, we convey all of the certain digits, and then the last digit that we report is what we call our first estimated digit. And they have done that exactly here, okay? So for group number 1, their certain digit was the ones place, and their first estimated digit was the tenths, whereas group number 2, all they had was an estimated digit, and that was in the ones place, okay? Okay, so these are group number 1, group number 2. How would you actually go about doing this when you're making measurements in that, okay? So let's say that you went into the lab, and you wanted to weigh out the mass of a pistachio, okay? And you had 2 different scales or 2 different balances to do that with, okay? So on the first side, or on the left side, on our left balance, note what the lines indicate, right? So we have a little pistachio, it's on the balance, and this guy is a 10, whereas this guy is a 0. So what are each of those individual lines telling me? What decimal place? Or not even decimal place, but just what place? Ones, right? So these guys, these lines, are telling you certain digits. If you have a line, that digit is certain. Okay? So with respect to this little pistachio on this scale, we know for certain that it is 1, right? So this guy is 1, this guy is 2. So we know with certainty that it's between 1 and 2, so it's at least 1 gram. Now comes our first estimated digit, okay? So let me erase this. Where do you think this guy lies with respect to the position between 1 and 2? Does it matter what I put here? Is it up to the observer? Yes, okay? So let's say I look at this and I say, okay, I think that line is a little bit closer to 1, so I'm going to estimate this to be 1.3 grams, okay? With respect to this scale, this was certain because they gave us lines for it. This was my first estimated digit, okay? All right, so now let's move over to our right scale. Same pistachio, measuring the exact same weight, okay? So what we're looking at here are these guys down here, okay? Note that we have lines here, here, so we have 0, we have 1, we have 2. What are the little lines in between those? What decimal place are they indicating for us? The tenths place, right? So now we have certainty with respect to the ones place. We also have certainty with respect to the tenths place, okay? So when I go in here, I say, okay, it's between 1 and 2, got that, so it's 1. Now we say 1.1, 1.2. So I can say with certainty it is 1.2. Now I get to estimate that last digit. That's the last digit I get to report with respect to this measurement, okay? So I'd say, oh, it's pretty close to the 1.3, so I'm going to go with 1.28 grams. Again, this is our estimated digit, and these are our two certain digits, okay? All right, so anytime an instrument gives you a line, it's a certain digit. What about something like measuring volume, something like this in a graduated cylinder, right? Same thing with respect to the volume measurements. This is measuring in milliliters, except how would you measure the volume of a liquid like this that has kind of this concave little surface, right? So with water, when you put it in a graduated cylinder, what does it form? A meniscus, right? So how do you measure a volume if you have a liquid that forms a meniscus? Where do you measure it at? At the bottom of the meniscus, okay? So again, for this guy, I have certain digits with respect to the ones place, right? What else does my certainty lie? What decimal place? Tenths again, so where would I be estimating to? The hundredths, right? So my measurement here would have to be reported to the hundredths place because that's my first estimated digit. And again, I would measure it right at the bottom of the meniscus, okay? I'm going to let you guys think about this one because that's part of the activity. So I'm not going to actually give you the volume for this. Okay, so that's great. That's how you make measurements in chemistry, right? So super interesting. But now, let's say you spend all this time being very certain with respect to your measurements, and now you're going to take your measurements and you're going to go do a calculation with them, okay? So let's say that you went into the lab and you wanted to calculate or measure the density of a substance, okay? Again, we've already talked density is mass per volume, okay? So you take your substance and you go in and with whatever degree of certainty the instrument is, you measure the mass at 1.35. Very careful to report the correct amount of certainty, and then you measure the volume equal to 5.3 milliliters, okay? So you're very good scientists, you're very good at reporting the correct amount of certainty with respect to your measurements. Now, you put that in your density calculation, so 1.35 divided by 5.3 mils, and you get out something that looks like this, 0.254716 ... right? So you've taken measurements where you have a certain degree of certainty, you've made a calculation with them. How do I know how many digits I'm supposed to report with respect to this calculation? All right, should I report all of them? If the reader of my report says, look at all of these digits, this person must be very, very, very certain with respect to the mass and the volume measurements. Would that be correct? Would that be accurate? No, okay? So this is the point of sig figs. This is the point of significant figures. It's knowing how many digits you should be reporting in an answer that utilizes numbers in a calculation, okay? It's all going back to spend all this time talking about certainty and measurement. We also have to kind of convey that certainty when we utilize these measurements to make calculations, okay? Okay, so first step in using sig figs is knowing what is actually a significant figure. How do you know if a number is significant or not, okay? So there are going to be a few rules with respect to counting the number of significant figures, knowing whether something is significant, okay? The first rule is the easiest. All it says is all non-zero digits are significant, okay? So if it's not a zero, it's a significant figure. You should count it as a sig fig. That's the easiest one to remember. The hassle comes in what happens when you have a zero, okay? So the first rule with respect to zeros is that all interior zeros, so these are going to be zeros that are sandwiched between non-zero numbers, are significant, okay? So for example, if I had this guy, 408, how many significant figures is in that number? 3, right? I have 2 non-zero numbers and I have a 0 that's sandwiched between them, so they are all significant. Same thing for this guy. I have sandwiched zeros. How many sig figs do I have in this number? So 5. I've got 1, 2, 3, 4, 5 different numbers. So there are 5 significant figures, okay? Number 3, leading zeros. What happens if we have zeros that are leading a number? Leading zeros are never significant, okay? So anytime we have any type of leading zeros, all they are doing is serving to locate the decimal point, right? What would be a better way to write this anyways? Scientific notation, or convert with the prefix multipliers, right? So these guys are never significant. You never count them with respect to sig figs. So how many significant figures would this number have then? 3. And what about this guy? 3. Never count leading zeros. Okay, so last few things. Trailing zeros. So zeros that trail non-zero numbers, okay? First one, if we have a trailing zero that comes after a decimal point, they are always significant, okay? So an example would be this guy. We have a bunch of trailing zeros. They come after a decimal point, so all of these are significant figures. So how many sig figs would I have for a number like this? 5. And what about something like this? 5 as well. These zeros all come after a decimal point, so they are all significant. Okay, so then trailing zeros before a decimal point, but after a non-zero number, something like this, something like these guys, these are also significant figures, okay? Again, they're sandwiched between non-zero numbers, so you should just utilize that non-zero thing, or the sandwich one at least, to count these as significant figures. So this guy would have 5, and this guy would have 1, 2, 3, 4, 5, 6 sig figs, okay? Now the last one is always kind of the one people are like, what am I supposed to do with this? So it's something like this, where we have trailing zeros before an implied decimal point. This is ambiguous. You cannot know, just given this 1200, whether these zeros count or not, okay? And so if you're given a number like this, you would just send it back to the measurer and say, hey, give me some idea about the certainty in this measurement. Again, what would be a better way to write 1200? Yeah, so it'd be better if we converted to scientific notation, and then we could accurately convey how certain we were with respect to our measurement, okay? So this guy's ambiguous. If we converted to scientific notation, we could accurately convey this. Again, we would not count these in sig figs, so this guy would have 2, this guy would have 3, and this guy would have 4. Another way to do this, if you didn't want to do that, was you could put a decimal point right at the end of the number. If you did that, then you'd be indicating that all of these guys were significant, so this would have 4, because you put this guy there, okay? Okay, one more thing. Those are all of the rules. What happens if I have what is called an exact number? So an exact number is going to be an actual number, right? So let's say I have 5 people. That's an exact number. So 5 people. Exact numbers are essentially infinite in their amount of significant figures. There's no uncertainty in measurement. So you could say they have an infinite amount of sig figs, or no uncertainty, and you don't actually utilize them in figuring out how many sig figs you should be answering with, okay? Again, if you counted 5 people, how certain are you with respect to your measurement? There's 5 people, right? There's no 5.1, there's no 5.2, etc. Another example of an exact number would be integers that are part of equations, right? So if I wanted to measure the radius of something, or determine the radius of something, and I had the diameter, I would divide by 2. You would not use this 2 to count sig figs, okay? Just like you would not use the 5 people to count sig figs. Also, defined quantities, like these conversion factors that we use for the prefix multipliers, you do not utilize those at all to count sig figs as well. Okay, so that's quick. A quick little question to make sure you guys are getting this. I want to know how many sig figs are in the following numbers. Okay, so go ahead and get your answers in. We'll go over these. Most of you are getting this correct. That last one's causing some people problems. So for number 1, how many sig figs are there? 2, right? The leading zeros don't count, so only the non-zero numbers count. So there are 2 here. What about number 2? 5, right? So these are trailing zeros that come after a decimal place. So they do count. We would count them as 5. What about number 3? 4. So we have a 0 that is sandwiched in between 2 non-zero numbers, so it gets to count. And then what about 4? This is kind of a, yes? Yeah, so you're correct. I know it shows up as incorrect, but again, I'm not counting these for correctness. This is an exact number, so you don't actually utilize it to count sig figs. This could be unlimited if you wanted a correct answer in this, or I put infinite. If you put infinity, that's correct as well, okay? So again, there's no uncertainty in this measurement, so it's an unlimited amount of significant figures, okay? All right, so again, what's the point of all of this? It's kind of boring. Nobody likes sig figs. Make all of this effort to convey the correct amount of certainty in our measurements. We have to convey that also when we're doing calculations, okay? So this is why we teach you sig figs. There are going to be 2 rules that you have to be aware of when you're utilizing measurements to make calculations. And it's going to depend on whether or not you're doing multiplication and division or whether or not you're doing addition and subtraction, okay? So the first rule is one that people always remember, never forget, It's the only one they remember, unfortunately, too. Okay, and it's the multiplication and division rule. And so what it says is that when you multiply and divide, your answer of that multiplication and division should have the same number of sig figs as the figure with the least amount of sig figs that you're using for the actual multiplication and division. Okay, so for example, if I had this number and I wanted to multiply all these guys together, I would get this as my calculation answer, right? But I want to report this answer with the correct amount of certainty, right? So to do that, because this is multiplication and division, I would go in and count, all right, this guy has 4 sig figs, this guy has 5 sig figs, and this guy has 2. So my answer has to have the same number with the fewest amount, right? So who is the fewest? 5, 4, 2? 2, right? So my answer also has to have 2 significant figures, okay? So I'd look at my answer, I'd say, oh, this is 1, this is 2, so my answer is 6.7, 2 sig figs, okay? Same thing with division. If I have a number with 5 sig figs, a number with 3, I'm dividing them, my answer has to have the same number as the 3 sig figs. So my answer has to be to 3 significant figures, okay? Now, the hassle always comes in with respect to addition and subtraction, right? So this guy's easy. You count the number of sig figs. The answer has to have the same number as the fewest number. Addition and subtraction is slightly different. With addition and subtraction, we aren't going to actually count the number of sig figs in each individual number. Instead, we're going to be limited by the number that is reported to the least amount of decimal places, okay? So what do I mean by that? Let's say we have these 3 numbers that we are adding together, okay? This first number, what decimal place am I reporting my measurement to? So this is tenths, hundredths, this is the thousandths place, right? So this first number is reported to the thousandths. What is this guy? What is this reported to? To the hundredths. What about this guy? What is it reported to? To the 10,000ths, right? Who is reporting to the least number of decimal places? To the hundredths, this guy, right? So my answer has to be reported to that same decimal place, okay? So a nice little way to do that is to draw a line where the digit with the least amount of decimal places essentially ends, and my answer has to be to that exact same decimal place, okay? So for this guy, I would add these guys together, but my answer has to be reported to the hundredths place because of that guy in the middle, okay? Same thing for subtraction. I've got 5.9, which is reported to the tenths. I've got 0.0 or 0.221, which is reported to the hundredths. Because of this tenths place, I can only report my number to the tenths place, okay? Note what I do here, right at the end. I have 5.679, and I have to report this to the tenths place. So what do I do? Instead of saying 5.6, what do we do instead? We round it up. Okay, so rules for rounding, because sometimes they change, and I just have to let you know about how I go about this. So rules for rounding in here, if it's a 5 or above, you're going to round to the number up. If it's a 4 or below, you're going to round to the number down. Some people are different, and that's why I have to actually specify this, okay? So for example, if I have these numbers, and I want to round these guys to 2 sig figs, 5.37 to 2 sig figs, what would I round to? This would be 5.4. What about 5.34? What would the answer be here to 2 sig figs? 5.3, 5.35, 5.4. We would round up because of the 5. And note that when we're rounding, we're only looking at the digit right next to what we're going to, right? So even this is 5.349. What am I going to round to? 5.3, okay? It doesn't matter that this 9 would try to round it up to 5. You're only just looking to the direct right of wherever you're rounding to, okay? All right, so one more thing, and I'll let you guys get started. So that was easy. We have rule number 1, rule number 2, multiplication, division, addition, and subtraction. What if we're having to do multiple different types of arithmetic operations? How am I going to be able to keep track of my sig figs, okay? So number 1, just like you would do for the actual operation, you're going to use order of operations, right? So order of operations, please excuse my dear Aunt Sally, just as a reminder. And then number 2, as you're going through this, you don't want to start rounding too early. If you do, you're going to start introducing calculation errors because you're rounding and it's messing up all of your numbers, okay? So you don't want to round until the very end, but you do want to keep track of all the significant figures as you move down, okay? So what do I mean by that? Let's say we're doing this calculation here, okay? We've got a number multiplied by a number multiplied by something in parentheses. What am I going to do first? I'm going to do the parentheses first, right? So in the parentheses, what is happening? I'm subtracting, right? So I have a number, 5.489, and I'm subtracting from it 5.01. If I was going to report this number, this answer, to the correct number of decimal places, where would I report it to? The hundredths place, right? Because this guy is limited to the hundredths place. So when I do that, I get 0.479. I'm not going to round here, right? Because if I round here, I may introduce errors in calculations. What I am going to note is that this guy is limited to the hundredths place, okay? So I'm going to note that, but I'm going to move through with the same number for the remainder of the calculations because I'm not going to round to the end, okay? So now, after I've done the subtraction, I've got a number times a number times a number. So which rule am I going to use to figure out how many sig figs I have? The first rule, where we're counting the number of sig figs, and the answer is going to have this number with the fewest number. Sorry. So for that, I've got a number with 3 sig figs. I've got a number with 4 sig figs. What does this last number again have, even though we've written it as 3? It only has 2, okay? Because, again, of that original one. So 3, 4, 2, how many sig figs will my answer have if I'm multiplying? 2, okay? So we get a number, this is what it is, but we have to round this to 2 sig figs, so the answer here is 19. Okay, yes?
So when you're doing your calculations, when you're multiplying all 3 of them, and on the last part, the 0.479, for the sake of your calculations, you add that 9 in when you're multiplying.
Yes,
right?
yes.
But when you do your answer, that's where you take into consideration the 2.
Yes, exactly. Yeah, so keep the number, keep using it, but just note how many sig figs it has at that point in time that you're moving on. Okay, yes?
I just want to make sure, so when there are whole numbers in like an addition or multiplication, do you just have the significant figure of the number with a decimal?
So it'd be like, let's say we had 110, and we weren't certain with respect to this, and we were adding that to 9. If this was where this guy was limited to, then we would have to write, our answer would have to be to the hundredths place, right? So if I said, okay, I'm going to add 1.1 times 10 to the 2, which is 110, but we're denoting that the hundredths place, or the tens place, is where we're limited to, and we're adding that to 9, then my answer would have to be to the tens place. Sorry, I keep getting that wrong. So that would be 119. We would round up to 120. We would write that as 1.2 times 10 to the 2. Ignore that for the most part. If you have questions, let me know. Okay? But now I want to get started with the activity because it's using everything that we've done today and even stuff from last time. All right. Okay, so for A, what are we doing? What arithmetic operation are we performing? We're dividing, right? So multiplication and division rule, the answer is going to have the same amount of sig figs as the number with the least amount of significant figures, right? So for our first number, how many sig figs does this have? This has 5. And our second, how many does this have? 4, right? The 0 is trailing. So any type of trailing zeros after a decimal place count as significant figures, okay? So when we do this division, we end up getting 2.4485. Maybe there's some more numbers, but how many significant figures should my answer have? 4, right? So 4 would be this. This is an 8. The next number right to the right of it is a 5. So what do I need to do to the 2.448? I need to round up, okay? So the correct answer here would be 2.449 because this is a 5. Anything 5 and above, we're going to round up, okay? All right, so then B, most everyone got that, so that's good. B, what are we doing? We are subtracting, right? So this is going to be a completely different rule, right? We're not going to count significant figures. Instead, we're going to report to the same decimal place as a number with the least amount of decimal places, okay? So we're taking this number, which is reported to the tenths, hundredths, the thousandths place, and we're subtracting this number, which is reported to the hundredths place, okay? So when we subtract these, we end up getting 71.809, but what decimal place should I be reporting this answer to? Because this is going to the thousandths, this is going to the hundredths. Who are we limited by? The hundredths place, right? We're limited by this guy. And so we're going to report our answer to the hundredths place because of that. So the hundredths place is here. So now if I look directly to the right of my hundredths place, it's a 9. So what do I need to do to the digit? I need to round up. So this is going to be 71.81. This is the correct answer. Okay, so then the last one is multiple things, right? With respect to significant figures here, we're going to follow order of operations, okay? So when we're doing this, what parts of this little operation are we going to do first? The parentheses, right? And we're going to count sig figs coming out of the parentheses as if they were its own little thing, right? So we're multiplying in the parentheses. We have 1, 2, 3, 4, 5, 6 sig figs times 4 sig figs. So how many significant figures should come out of those parentheses? 4, right? So I'm going to go ahead and write what happens here. We have a 29.2677, on and on and on, right? I'm going to note, though, that with this number coming out of the parentheses, we are actually limited to 4 sig figs, which is right here, right? Why don't I round this right now to 4 sig figs? Because I'll introduce error in measurement or introduce error in calculation if I round too early, right? Again, we're going to use the entire number, but we're going to note that this actually only has certainty to the hundredths place because of the 4 sig figs. So now we're going to subtract 4.9003. Now we're doing a subtraction problem, so we're limited to the decimal place now. So this guy reports to the tenths, hundredths, thousandths, 10,000ths place, whereas this one we're limited to the hundredths place. So what is my answer going to be reported to? The hundredths place as well, okay? So because of that, we end up getting a 24.3674. We can only report our answer to the hundredths place, so we're going to round that up. We'll end up with 24.37. Okay. So sig figs are great. They're awesome. You're going to do great at them. You're going to remember all the rules. It's going to work out really well, okay? All right, so just as a note, this week in lab, you guys will be making a bunch of measurements of stuff, right? What we're really looking for is that you guys are using the correct number of significant figures when you're doing calculations, and that you're writing your measurements with the correct amount of certainty given the instrument that you're using, okay? So sig figs are going to be graded very harshly on this first lab because it's essentially the purpose of it. So if you ever have any questions, please feel free to ask me or your lab instructor as well to make sure that you're using the correct number of sig figs, okay? Okay, so a couple of things to note before we get started with the remainder of Chapter 1 and then we move on into Chapter 2. You do have homework, right? Homework number 1, which covers Chapter 1, is due on Sunday. That's Sunday at 11:59, so at midnight, okay? So please do the homework before Sunday. Another thing, so normally I would like to have an activity on Thursday, but we're not going to get through enough of the lecture to do that. So the activity is going to be pushed to Tuesday of next week, okay? So our next activity will be 9/4, that's Tuesday of next week, and it will be dealing with something called nomenclature, okay? All right, so we'll talk about that more when we get to that. Do the homework and answer your questions on Podia. I've noticed that a lot of people are just writing questions from the homework and they're just posting that. You know, if you do that, it's okay, but just maybe put in a little bit of why you don't know the answer as opposed to just trying to get the answer, right? So if you say, oh, how many sig figs should this answer be reported to? I don't understand the rules of sig figs. then that would be okay as just saying, essentially copying and pasting the question from the homework. That's maybe not the best thing to do, okay? Okay, so good. I'm glad to see people are using Podium. Okay, so going forward, the last little bit of this chapter deals with a couple of different aspects with respect to measurement. Again, we're going to keep hitting measurement, and then we'll talk at the very end about dimensional analysis, okay? All right, so frequently, when we go into the lab, let's say we want to measure the mass of something, okay? Do you think it will be sufficient to go into the lab and measure the mass of something once? Do you think that's what we like to do with respect to science? No, right? So we like to make a bunch of replicate measurements, okay? This kind of gives us an overall idea that if we made an error in our original measurement and we make another one, it'll essentially kind of alleviate that error that we made in the original. So what we do is we frequently go in, make multiple different measurements of the same thing over and over and over, okay? So a couple of different things, or two different terms, are going to come out of making these replicate measurements in the lab, okay? The first one is called precision, and the second one is called accuracy, okay? So we use these terms kind of synonymously, but they're not the same thing. They mean two different things. So precision is essentially how good your individual replicate measurements agree with one another, right? So if you make a bunch of measurements, how close are they actually to each other? And then accuracy is going to refer to how much they deviate from the actual value of the thing you're looking at, okay? So again, we go into the lab. Let's say we measure the mass of something 3 different times, okay? So let's say we measure the mass and we get 5 grams one time, we get 4 grams another, and we get 5.5 grams a third time. How are we probably, if we want to say, oh, this is the mass of this thing, how are we usually going to probably try to define that? How are we going to use these guys? We're going to say, oh, I'm going to pick this one and just say that's the mass of the thing. What do we usually do? We'll usually take the average, right? So the average of our replicate measurements will be essentially what we're reporting for the real value, okay? So precision is going to reference how close these guys are with respect to one another. The way we will typically measure this, and the way that you will measure this in the lab, is via something called standard deviation. So standard deviation is a measurement of essentially how close your values are with respect to one another. For accuracy, we will measure something different, right? So again, we'll be comparing the average value that we have to the true value of the thing, and we usually measure that with something called percent error. And again, you guys will go through this when you get to the lab, but we usually measure precision via standard deviation and accuracy via percent error, okay? Okay, so again, going through, let's say you do have a student, right? So student A, and you have another student B, and you have another student C. And they all 3 go in and take a 10-gram weight, and they measure the mass of it, and they measure it 4 times. Okay, so we plotted these numbers of each individual trial for each individual student. If you look at these numbers as they are written, is it easy to see who's accurate and who's imprecise, or who's precise and who's inaccurate? No. So just looking at numbers, sometimes it's hard to see accuracy and precision. A better way of kind of denoting this is utilizing something like a bar graph. Okay, so in these bar graphs, we have listed student A, student B, and student C, and they're each individual trial. They're each individual measurements for each trial. And then we've also listed their average. So the average is in red, and then the true mass of the thing is in blue. Okay, so the true mass is 10 grams. So when you look at student A, how precise is student A? All right, so notice that we have the first measurement way up here, second measurement is way down here, third is here, and then fourth we go way back up again, right? So how precise is that? How closely are those measurements with respect to one another? They're not very close, right? So student A is imprecise. Their measurements are all over the place, okay? What about accuracy? So the average here is 10.13, but we know that the true mass is 10 grams. How accurate have they been? Ideally, this isn't very good, right? If it's 10 grams, it's not that much of a mass. So this guy is also very inaccurate, right? Because the average deviates fairly significantly from the true value, okay? All right, so compare student B. So student B has an average of 9.79, so not very accurate, right? But how precise is student B? How closely are each individual trial with respect to one another? We've got here, 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 here. They're all fairly close with respect. So student B is going to be considered fairly precise. And again, that would be measured via the standard deviation of each individual trial. Okay, then student C, we've got 4 different measurements again. How precise is student C? Pretty precise, right? These guys are pretty close with respect to one another. And then how does the average compare with the true value? Fairly good, right? So the average is 10.01 grams, true value is 10 grams. So student C is both precise as well as accurate. So student C is a model student, okay? All right, so what types of error could lead to both the problems that student A saw and the problems that student B saw, right? So student A was both inaccurate and very imprecise, okay? So the type of error that leads to imprecision is usually called random error, okay? So if we went back and we looked at student A's actual measurements, you would note that one of them was really high, one of them was really low, one of them was high, one of them was low, right? So for random errors, you have an equal probability of being too high or too low. It's just random, okay? And usually, who do you think's the fault of random error? Probably the student, right? So student A probably was not a very good scientist when they went into the lab, okay? All right, another type of error is called systematic error, okay? So systematic error specifically is part of the system that you're looking at, right? So student B, their measurements were very precise, right? They were right on top of each other. There was no really deviation from the actual measurement that they were making. But what was the problem with student B? They were inaccurate, but why? All of their measurements were what? They were too low, right? So they all measured too low compared to the actual value. And so if you have a tendency to always be too low or always be too high, that's probably something wrong with the instrument, okay? So student B, we're seeing systematic error because all of the measurements were essentially too low, okay? So this probably, there's something wrong with the instrument, and the balance needs to be probably calibrated or something like that, okay? Okay, all right, so random error versus systematic error. All right, so this last little bit, I'm going to go through just a little bit of a refresher with respect to dimensional analysis. So I've kind of already talked about it. I've alluded to dimensional analysis, but I haven't really sat there and said this is how you're going to use dimensional analysis. So with respect to chemistry, a lot of times we are going to be doing conversion problems, right? Well, we will be converting from one thing to another thing, okay? And so frequently we will want to employ something called dimensional analysis to help guide us in how we convert from one thing to the next. Well, what is dimensional analysis? How would you use it, right? With dimensional analysis, you're going to be utilizing units to help guide you in figuring out how to convert stuff, okay? So you should consider units like algebraic quantities, right? If we had an algebraic quantity like x and I divided it by x, what am I going to be left with? 1, right? These guys essentially cancel. If I had something like xy and I divided it by x, what am I going to be left with? Y, right? Same thing with units. If I have a centimeter and I divide it by a centimeter, it's going to cancel, etc. Okay? Okay, so what do we need with respect to dimensional analysis type problems? So the first thing you need is what is called a unit equation. Okay, this is going to essentially denote an equivalency of units, right? An example of that is this unit conversion here, right? We give this originally when we talk about lengths or meters, but a centimeter or 2.54 centimeters is equal to 1 inch, okay? This is our statement of equivalency, okay? We can use these unit equations and convert them to conversion factors, okay? So conversion factors are going to essentially take that unit conversion or that unit equation and turn it into a fractional quantity, right? So for example, for this guy, turning this into a conversion factor, we could turn it into 2.54 centimeters over 1 inch, or we could convert this into 1 inch over 2.54 centimeters, okay? So we're taking a unit equation and we're converting it to a conversion factor, okay? And so then in dimensional analysis, what we'll usually do is we will have our given unit, which is what you're given, and when you put in your conversion factor, you want to do so in a way that the given unit is on bottom, so it cancels the given unit, and the desired unit is on top, so that you end up with the desired unit, okay? Okay, so best thing to do with respect to dimensional analysis problems is to just do them, okay? So we'll go ahead and do a couple of different examples of how you would utilize this. So for example, what if I wanted to convert from 165 pounds to kilograms? All right, so I have my given as 165 pounds. What would I need to convert to kilograms? I need the unit equation, right? What is the equivalency between pounds and kilograms? So the unit equation here is 1 kilogram is equal to how many pounds? Yes. Right, so 1 kilogram is equal to 2.2 pounds, okay? That is our unit equation, okay? So converting that into a fractional or a conversion factor, I want to cancel my pounds on top, right? So who am I going to put on bottom? What part of this unit equation? I want to put the pounds on bottom, and I want to put the number that is associated with the pounds, right? So this is 2.2 pounds is equivalent to how many kilograms? To the 1, right? So now, when I multiply and divide, the pounds are going to cancel. I'll be left with units of kilograms. I'll take 165 and divide by 2.2, and that gives me 75.0 kilograms. How many sig figs should my answer be to? 3, because there are 3 here, right? And this is what we're actually measuring. So my answer should be reported to 3 sig figs. Okay? Okay, so another example, sometimes you'll have to use multiple different conversions, right? So let's say I wanted to convert 1.76 yards to centimeters. I could look up the direct conversion for that, right? But instead, let's say I knew that 36 inches equals 1 yard. What is the relationship between centimeters and inches? Just said it. So how many centimeters equals 1 inch? 2.54, okay? So now in converting this, I'm going to start with my given unit. What is my first conversion? From yards to what? Inches. My relationship, yards goes on bottom. How many centimeters or how many inches for every 1 yard? 36. And then now what do I need to do? I'm converting from inches to what? Centimeters. So for every 1 inch, how many centimeters do I get? 2.54. So now when I divide and multiply everything, my yards cancels, my inches cancels, I'm left in units of centimeters. And then how many significant figures do you think my answer should be reported to? 3, right? So when we multiply this guy out, we get 160.9, which when we round, we'll get 161 centimeters. Super easy, right? Kind of. There's only one more little thing that I just want to kind of remind you of or make you aware of. And that's what happens when we're dealing with units raised to a power, okay? For example, let's say that I had a volume, right? I had 2.11 inches cubed, and I wanted to convert this to centimeters cubed, okay? So again, this is a unit raised to a power. I've got 2.11, and I'll go ahead and write my inches cubed. I know my conversion between inches and centimeters. It's 2.54 centimeters is equal to 1 inch. So I go ahead and draw my little railroad tracks. I'm going to put the inch on bottom, and I'm going to put the centimeter on top, and I'm going to go ahead and write the fractional amount, the conversion factor, right? What would happen if I just did this? What would be my units if I just took my inches cubed and I did one little conversion factor for centimeters to inches. So we'd be left in units of inches squared centimeters, right? Is that converting to cubic centimeters? No. If I want to convert to cubic centimeters, how many of these conversion factors do I need to put in there? 3, right? So I could do 2.54 centimeters to 1 inch, and then I could do another, let me get rid of this guy, another 2.54 centimeters to 1 inch, right? So I could do that 3 separate times, and I would multiply the numbers out 3 separate times, and again, that would leave me with centimeters cubed, and I'd get rid of all of my inches, okay? How else could I represent doing this conversion 3 different times? So another way I could write this is 2.11 inches cubed, and when I put my conversion factor in, I could say 2.54 centimeters for every 1 inch, but I could also just cube it directly, right? Whatever unit I have, or whatever power I've raised this unit to, when I put the conversion factor in, I need to also raise the number of the conversion factor to that exact same power so that I cancel it out, okay? So it's not just the unit, it's also the 2.54 that has to be cubed as well. Okay, so when we do this, we end up getting another number. How many sig figs probably should the answer be in? Probably 3. So the answer here is 34.6. And again, you're multiplying that 2.54 by each other 3 times or raising it to the 3rd power. Okay, all right. Any questions? No. Okay. So we're done. That's it with chapter 1.